Hello and welcome to another lecture on electrical circuit theory. Today we will be solving a simple resistive network using loop analysis. Loop analysis is one of the techniques of solving KVL equations by formulating loops within the network. So in my previous lecture on KVL, I explained the physical significance of Kirchoff's voltage law. So if you haven't seen that lecture, you can click on this link. So for loop analysis, the first thing we have to do is to identify the number of loops that we need. So the criteria for doing that is that each element within the network should be encompassed at least one. So for example, I1 includes R1 and R2, and I2 includes R3, R4, and R2, and thus all elements within the network are encompassed by these two loops. Now I can also have a loop like this. So I can have I1 and I can call this as I2 instead of this green one. And here as well, I am encompassing all the elements within the network by these two loops. And hence, two loops suffice to solve this network. Once we have identified the number of loops, the next thing we have to agree on is the polarity convention. So if I have a resistor like this, and if current is entering, then I can agree that where the current enters, the polarity is positive, and where the current leaves, the polarity is negative. You can also have it the other way around, but this is the most commonly used polarity convention for solving electrical networks, and we will stick with this one. So let's apply this polarity convention to our network here. So this current I1 is in the direction given by this arrow. So it is entering R1 here. So I would have a positive here and a negative here. Then it enters R2 here, so positive here and negative here. The same polarity conventions I can write for I2. So it enters R3 at this point and leaves here. So it's positive, negative like this. And R4 is positive and negative like this. For R2, it is the opposite of I1. So it is entering at this point and leaving at this point. So the total current would flow from top to bottom if I1 is greater than I2. Only then I1 minus I2 would be flowing in the downward direction. So the current flowing in the downward direction would be I1 minus I2. On the other hand, if I2 is greater than I1, then the total current flowing through R2 would be in the upward direction, and this would be I2 minus I1. The next thing we have to do is to write KVL equations. The next step is writing KVL equations. So we know the drops across all the resistors. We have a 20-volt battery with its negative connected to ground. So this is 20 with a polarity like this. Now I can just follow the loop and take notice of all the polarities while I'm entering each element. So I enter this battery from here. You can start from anywhere, but I'm starting here from this battery. I counter a negative, so I write negative 20. Then I go to my resistor R1 and I see a positive. So I write the drop across R1, which is I1 times R1. Then we have already seen that the current flowing downwards is I1 minus I2. So I see a positive, so plus I1 minus I2 times R2 equal to 0, and this is my first equation. Similarly, I can write a second KVL equation. The drop across R3 would be I2 times R3 plus I2 times R4 plus the current flowing in the upward direction is I2 minus I1 times R2 equals to 0, and this is my equation 2. So now we have two equations and two unknowns, I1 and I2. So we can solve this by elimination. So let's simplify these two equations further. I can take I1 common from the first equation, so it would be I1 into R1 plus R2 minus I2 times R2 equals 20. Similarly, equation 2 can also be simplified. I can group all the terms with I2, R2 plus R3 plus R4 minus I1 times R2 equals to 0. Let's call these equation 3 and equation 4 respectively. And now we can plug in the values of the resistors and the battery voltage and solve this network. So this would be I1 times R1 plus R2 would be 15 minus I2 times 10 is equal to 20. If I divide by 5, I would have 3 times I1 minus 2 times I2 equals to 4. Let's call this equation 5. And equation 4 can be written as R2 plus R3 plus R4 would be 20 minus I1 times 10 equals to 0. So this can be written as 2 times I2 is equal to I1. This is my equation 6. So in the method of elimination, we write one variable in terms of the other. So I1 here is expressed in terms of I2. So we plug this value of I1 in equation 5 and get the value of I2. So this would be 3 times 2 times I2 minus 2I2 equals to 4. This would then become 4 times I2 equals to 4, and I2 would be 1 ampere. Now that we have the value of I2, we can plug it in 6 and get I1. I1 would then be 2 times 1 or 2 amperes. So this is the method of elimination for solving simple networks, but we'll also look at the method of matrices for solving complex electrical networks, and I will cover that in an upcoming lecture. That way it is more convenient to solve complex networks like a power system network, for example. So that's all for today, and in the next lecture we would look at branch current analysis, which is also another method of solving KVL equations, and that would be especially useful when we have a current generator. So in this network we only had a voltage generator in our network. So we'll see how branch current analysis can help us when we have current generators in the network. Thank you very much, and see you in the next lecture.